Hello, students. Welcome back. Have you ever wondered how atoms come together to form the world around us? It's all about bonds, and today we are diving into one of the most fundamental ideas in chemistry, valence bond theory. Imagine two hydrogen atoms floating in space, each with a single electron. When they come close to each other, their electrons begin to interact. This interaction leads to the formation of a bond, creating a stable hydrogen molecule, H2. But why do the atoms stay together? That's what valence bond theory helps us understand. In simple terms, valence bond theory explains how atoms bond by overlapping their atomic orbitals. This overlap allows the electrons to pair up, lowering the energy of the system and making the bond stable. While earlier theories like Lewis structures gave us an idea of how atoms bond, they didn't explain the strength or length of these bonds or why some molecules have specific shapes. That's where valence bond theory steps in. This theory was first introduced by Hitler and London in 1927 and later expanded by Linus Pauling. It shows that the strength of the bond depends on how much the orbitals overlap. The greater the overlap, the stronger the bond. So, let's begin our journey into the world of orbitals and bonds.
Now, let's explore how exactly these bonds form. When two hydrogen atoms approach each other, their atomic orbitals, like the 1s orbitals in hydrogen, begin to overlap. Picture this. As the atoms get closer, attractive forces start pulling them together. The positive charge of the nuclei attracts the negative electrons. But there's also a repulsive force when the like charges, the positive nuclei and the negative electrons, get too close. At some point, these attractive forces outweigh the repulsive ones, and the atoms settle into a position where the total energy of the system is minimized. This is the sweet spot where the bond is formed. The electrons in the overlapping orbitals pair up, creating a stable bond between the two atoms. In the case of hydrogen, the bond length is about 74 picometers, and the bond is held together by the attractive force between the electron pair and the nuclei. This is a great example of how the overlap of atomic orbitals leads to the formation of a covalent bond. As you can see, the balance between attractive and repulsive forces is what makes the bond stable. Now that we understand how bonds form, let's talk about their directionality. When atomic orbitals overlap to form a bond, the orientation of that overlap matters. In simple molecules like H2, the bond is straightforward. But in more complex molecules like methane, CH4, the bond formation is more intricate. In CH4, carbon has 4 valence electrons, and each one bonds with a hydrogen atom. But here's the catch. The bond angles in methane aren't just random. They are tetrahedral, with bond angles of 109.5 degrees. This tetrahedral shape is the result of the specific overlap of carbon's sp, 3 hybrid orbitals with the 1s orbitals of hydrogen. The directionality of the bonds in CH4 is what gives it its unique geometry. So, valence bond theory doesn't just explain how atoms bond, it also tells us why molecules have the shapes they do. Next, let's break down the two types of covalent bonds: sigma bonds, and pi bonds. Sigma bonds are the most common and strongest type of covalent bond. They form when atomic orbitals overlap end-to-end along the internuclear axis. That's the line connecting the nuclei of the two atoms. Imagine two 1s orbitals coming together. This end-to-end overlap results in a sigma bond. Pi bonds, on the other hand, form when atomic orbitals overlap side by side, above and below the internuclear axis. This type of bond is weaker than sigma bonds because the overlap is less extensive. You'll find pi bonds in double and triple bonds, like in the molecule of ethene, C2H4. In this case, the sigma bond forms first, and then the pi bond forms from the side-by-side overlap of p orbitals. So, whenever atoms form a bond, you have to consider whether it's a sigma or pi bond, as this will affect the molecule's stability, strength, and even its ability to rotate around the bond. Let's take a deeper dive into hybridization, a key concept in understanding molecular geometry. When atoms bond, sometimes their atomic orbitals don't quite match up. For instance, carbon in methane, CH4, has an electronic configuration of H2S2 but when carbon bonds with 4 hydrogen atoms, its orbitals mix to form 4 equivalent sp3 hybrid orbitals, which then overlap with the hydrogen's 1s orbitals to form stable CH bonds. Hybridization helps us explain why methane has its tetrahedral shape. The 4 sp3 hybrid orbitals of carbon arrange themselves as far apart as possible, resulting in bond angles of 109.5 degrees. The concept of hybridization is critical not just for methane, but also for other molecules like ammonia, NH3, and water, H2O. So, hybridization is what allows atoms to form bonds in specific, predictable geometries. Without it, we wouldn't be able to explain the shapes of molecules like CH, 4, NH, 3, or H2O. Let's quickly recap what we've learned about valence bond theory. First, we saw how orbital overlap leads to the formation of covalent bonds. Then, we explored the directional properties of bonds and how they shape molecules like methane. Next, we discussed the difference between sigma and pi bonds. Sigma bonds are stronger and form first, while pi bonds form second and add additional bonding strength. Finally, we delved into hybridization, which explains the geometries of molecules like CH, 4, NH, 3, and H2O. So to sum up, valence bond theory isn't just about atoms connecting, it's about how these connections are made in specific ways, explaining everything from bond strength to molecular shape. I hope this session helped you see how chemistry is more than equations. It's the invisible force behind the world around us. Catch you in the next class with more fascinating reactions and real-world connections.